Solving NP-hard problems on trees. In section 10.1, we designed an algorithm for the vertex cover problem that works well when the size of the desired vertex cover is not too large. We saw that finding a relatively small vertex cover is much easier than the vertex cover problem in its full generality. Here we consider special cases of NP-complete graph problems with a different flavor, not when the natural size parameters are small, but when the input graph is structurally simple. Perhaps the simplest type of graphs are trees. Recall that an undirected graph is a tree if it is connected and has no cycles. Not only are trees structurally easy to understand, but it has been found that many NP-hard graph problems can be solved efficiently when the underlying graph is a tree. At a qualitative level, the reason for this is the following. If we consider a subtree of the input rooted at some node v, the solution to the problem restricted to this subtree only interacts with the rest of the tree through v. Thus, by considering the different ways in which v might figure in the overall solution, we can essentially decouple the problem in v's subtree from the problem in the rest of the tree. It takes some amount of effort to make this general approach precise and to turn it into an efficient algorithm. Here we will see how to do this for variants of the independent set problem. However, it is important to keep in mind that this principle is quite general, and we could equally well have considered many other NP-complete graph problems on trees. First, we will see that the independent set problem itself can be solved by a greedy algorithm on the tree. Then we will consider the generalization called the maximum weight independent set problem, in which nodes have weight, and we seek an independent set of maximum weight. We will see that the maximum weight independent set problem can be solved on trees via dynamic programming using a fairly direct implementation of the intuition described above, a greedy algorithm for independent set on trees. The starting point of our greedy algorithm on the tree is to consider the way a solution looks from the perspective of a single edge. This is a variant on an idea from section 10.1. Specifically consider an edge E equals to u v in G in any independent set S of G. At most one of u or v can belong to S. We'd like to find an edge E for which we can greedily decide which of the two ends to place in our independent set. For this, we exploit a crucial property of trees. Every tree has at least one leaf, a node of degree 1. Consider a leaf v, and let uv be the unique edge incident to v. How might we greedily evaluate the relative benefits of including u or v in our independent set S? If we include v, the only other node that is directly blocked from joining the independent set is u. If we include u, it blocks not only v but also other nodes joined to u as well. So if we are trying to maximize the size of the independent set, it seems that including v should be better than, or at least as good as, including u. 10.5. If t equals to ve is a tree and v is a leaf of the tree, then there exists a maximum size independent set that contains v. Proof: consider a maximum size independent set S, and let E equals to uv be the unique edge incident to node v. Clearly, at least one of u or v is in S, for if neither is present, then we could add v to S, thereby increasing its size. Now, if v is in S, then we are done. And if u is in S, then we can obtain another independent set S prime of the same size by deleting u from S and inserting v. We will use 10.5 repeatedly to identify and delete nodes that can be placed in the independent set. As we do this deletion, the tree T may become disconnected. So to handle things more cleanly, we actually describe our algorithm for the more general case in which the underlying graph is a forest, a graph in which each connected component is a tree. We can view the problem of finding a maximum size independent set for a forest as really being the same as the problem for trees. An optimal solution for a forest is simply the union of optimal solutions for each tree component, and we can still use 10.5 to think about the problem in any component. Specifically, suppose we have a forest F, then 10.5 allows us to make our first decision in the following greedy way. Consider again an edge E equals to UV, where V is a leaf. We will include node V in our independent set S and not include node U. Given this decision, we can delete the node V since it's already been included, and the node U since it cannot be included, and obtain a smaller forest. We continue recursively on this smaller forest to get a solution. So the algorithm is as follows. To find a maximum size independent set in a forest F, let S be the independent set to be constructed initially empty. Now there's a while loop. While F has at least one edge, let E equals to V be an edge of F such that V is a leaf. Then we add V to S, delete from F nodes U and V, and all edges incident to them, and while. Now, after we break out from the while loop, we return S. 10.6. The above algorithm finds a maximum size independent set in forests, and hence in trees as well. Although 10.5 was a very simple fact, it really represents an application of one of the design principles for greedy algorithms that we saw in Chapter 4, an exchange argument. In particular, the crux of our independent set algorithm is that the observation that any solution not containing a particular leaf can be transformed into a solution that is just as good and contains the leaf. To implement this algorithm so it runs quickly, we need to maintain the current forest F in a way that allows us to find an edge incident to a leaf efficiently. It is not hard to implement this algorithm in linear time. We need to maintain the forest in a way that allows us to do so on one iteration of the while loop in time proportional to the number of edges deleted when U and V are removed. The greedy algorithm on more general graphs. The greedy algorithms specified above is not guaranteed to work on general graphs because we cannot be guaranteed to find a leaf in every iteration. However, 10.5 does apply to any graph. If we have an arbitrary graph G with an edge UV such that U is the only neighbor of V, then it's always safe to put V in the independent set, delete U and V, and iterate on the smaller graph. So, if by repeatedly deleting degree 1 nodes and their neighbors, we are able to eliminate the entire graph, then we are guaranteed to have found an independent set of maxima size, even if the original graph was not a tree. And even if we don't manage to eliminate the whole graph, we may still succeed in running a few iterations of the algorithm in succession, thereby shrinking the size of the graph and making other approaches more tractable. Thus, our greedy algorithm is a useful heuristic to try opportunistically on arbitrary graphs in the hope of making progress toward finding a large independent set. Maximum weight independent set on trees. Next, we turn to the more complex problem of finding a maximum weight independent set. As before, we assume that our graph is a tree T equals to VE. Now we also have a positive weight WV associated with each node little v in capital V. The maximum weight independent set problem is to find an independent set S in the graph T equals to VE so that the total weight, the summations of WV, summing for all V in S, is as large as possible. First, we tried the idea we used before to build a greedy solution for the case without weights. Consider an edge E equals to UV such that V is a leaf. Including V blocks fewer nodes from entering the independent set. So if the weight of V is at least as large as the weight of U, then we can indeed make a greedy decision, just as we did in the case without weights. However, if WV, the weight of V, is less than WU, the weight of U, we face a dilemma. We acquire more weight by including U, but we retain more options down the road if we include V. There seems to be no easy way to resolve this locally without considering the rest of the graph. However, there's still something we can say. If node U has many neighbors V1, V2, V3, and so on that are leaves, then we should make the same decision for all of them. Once we decided not to include U in the independent set, we may as well go ahead and include all its adjacent leaves. So for the subtree consisting of U and its adjacent leaves, we really have only two reasonable solutions to consider, including U or including all the leaves. We will use these ideas to design a polynomial time using dynamic programming. As we recall, dynamic programming allows us to record a few different solutions to record a few different solutions through a sequence of subproblems, and thereby decide through a sequence of subproblems, and thereby decide only at the end which of these possibilities will be used. First issue to decide for a dynamic programming algorithm is what our subproblems will be. For maximum weight independent set, we will construct subproblems by routing the tree T at an arbitrary root R. Recall that this is the operation of orienting all the tree's edges away from R. Specifically for any node U not equals to R, the parent P of U is the node adjacent to U along the path from the root R. The other neighbors of U are its children, and we will use the children of U to denote the set of children of U. The node U and all its descendants form a subtree, TU, whose root is U. We will base our subproblems on these subtrees TU. The tree TR is our original problem. If U is not equal to R is a leaf, then TU consists of a single node. For a node U, all of whose children are leaves, we observe that TU is the kind of subtree discussed above. To solve the problem by dynamic programming, we will start at the leaves and gradually work our way up the tree. For node U, we want to solve the subproblem associated with the tree TU after we have solved the subproblems for all its children. To get a maximum weight independent set S for the tree TU, we will consider two cases. Either we include the node U in S or we do not. If we include U, then we cannot include any of its children. If we do not include U, then we have the freedom to include or omit these children. This suggests that we should define the two subproblems for each subtree TU. The subproblem OPT in of U will denote the maximum weight of an independent set of TU that includes U. And the subproblem OPT out of U will denote the maximum weight of an independent set of TU that does not include U. Now that we have our subproblems, it is not hard to see how to compute these values recursively. For a leaf U not equals to R, we have OBT out of U equals to 0 and OBT in of U equals to WU. For all other nodes U, we get the following recurrence that defines OBT out of U and OBT in of U using the values for U's children. 10.7. For a node U that has children, the following recurrence defines the values of the subproblems. OBT in of U is equals to WU plus the summations of OBT out of V, summing for all V, which is in children of U. OBT out of U is equals to the summations of the maxima chosen between OBT out of V and OBT in of V. After we take the maxima, we do the summation, summing for all V in children of U. Using this recurrence, we get a dynamic programming algorithm by building up the optimal solutions over larger and larger subtrees. We define arrays M out of U and M in of U, which hold the values OBT out of U and OBT in of U, respectively. For building up solutions, we need to process all the children of a node before we process the node itself. In the terminology of tree traversal, we visit the nodes in post order. To find a maximal weight independent set of a tree T, root the tree at a node R. For all nodes U of T in post order, if a U is a leaf that sets the values, then M of out of U is equals to 0 and M of in of U is equals to WU. Else, we set the values, that is M out of U is equals to the summations of the maxima chosen between M out of U and M in of U, M out of V and M in of V, summing for all V in children of U, or M in of U is equals to WU plus the summations of M out of V, summing for all V which is in children of U. And 4. So after we finish the for loop, we return the maxima chosen between M out of R, the root, or M in of R, again the root. This gives us the value of the maxima weight independent set. Now, as is a standard in the dynamic programming algorithms, we've seen before, it's easy to recover an actual independent set of maxima weight by recording the decision we make for each node and then tracing back through these decisions to determine which nodes should be included. Thus, we have 10.8. The above algorithm finds a maximal weight independent set in trees in linear time.